பாட்டு போட்டு வீட்டில்
So, good morning to one and all present here in this national webinar on magnetic smart materials, which is organized by the Department of Physics and Internal Quality Assurance Cell of Neshamani Memorial Christian College, Martanda. Before we begin today's webinar, I would like to give a small note, a brief note on the college and the Department of Physics in particular. As we all know, the Neshamani Memorial Christian College, Marthandam, was established in the year 1964. And at the same time, Department of Physics was one of the departments which was started immediately after the college was established. And at present, the department has a UG and a PG program in the aided stream, and a PG and MPhil program in the self-finance stream. And it also has a PhD program. There are 17 teaching staff members in the department. Among them, 8 of them are research guides. About 20 research scholars have completed their PhD dissertation. And 30 of them are pursuing their PhD at present. The department has a lot of research facilities also, like FTIR, UV, Raman, cyclic voltmeter, milli Q water purifier, hydraulic press, polarimeter, and so on. And it also possesses a large number of publications to its credit, that too with a high impact factor. Another very important thing is the department has an alumni association, and most of the alumnus, they are all placed in reputed institutions and organizations. The department also produces a number of university ranks every year, and they also every year they conduct NGP examination, that too in collaboration with the Indian Association of Physics Teachers of Kanpur. And the department has a well-established laboratory which provides individual individual apparatus for the students to do their practicals. So in addition to the central library, the department also has a separate library with a number of books and periodicals. And the department of the physics department of our college enjoyed a very glorious past, and even today it keeps its head high with great reputation among the affiliated colleges of Manoanmaniyam Sundarnar University. So today we are all very happy to conduct this webinar. And now I request the head of the Department of Physics and Research Center, Dr. Sheila Christie, to propose the welcome address. Sheila Christie, madam.
Okay, sir. Good morning to you all. It gives me great pleasure to welcome you all to this webinar on magnetic smart materials. Materials change their shape in a reversible and repeatable manner when exposed to a small magnetic field. Let me express my gratitude to our Almighty Father for his presence, guidance, and wisdom to organize this webinar. Next, I welcome our correspondent, Advocate Rajathurai, who is very active. I also welcome our beloved principal, who motivated us to conduct this webinar and is also presiding this meeting. Welcome you, sir. Our chief guest is Dr. Mahendran, Professor and Head, Department of Physics, Tyagarajar College of Engineering, Madurai. He has made a powerful contribution to the field of research and produced 17 PhDs. Over the last few decades, smart magnetic materials have become increasingly important in the design of products, and hence I'm sure we will be enriched by this webinar. On behalf of everyone who joined this webinar, I welcome you, sir. Next, I welcome Dr. Rachel J. Geeta, convener of this webinar, and Dr. Jabamalar, co-convener, who worked day and night to make this webinar a successful one. I also welcome IQAC coordinator, Dr. Tibi Thomas, who is coordinating this webinar. Next, I welcome my colleagues who are the part of this webinar. I also welcome the students, research scholars, and faculty members who has taken keen interest to join this webinar. Once again, I welcome you all.
Thank you, Madam, for the nice words that you have given as a welcome speech. Now it is the time for the presidential address. I think our principal has a small network issue. He was there in the meeting and he called me when I was giving the introductory talk. If he joins, we'll ask him to speak. I think he is not there at the meeting, so we'll not waste our time. So we'll go ahead with our program. So this is the time for the address of our important guest of the day. So before that, let me now invite Dr. Aruldas, the Associate Professor of the Department of Physics, to introduce our guest, Dr. Mahendran. Over to Dr. Aruldas.
Good morning to all. This gives me an immense pleasure to introduce our resource person, Dr. Manikyam Mahendran, Professor and Head of the Department of Physics, Tyagaraja College of Engineering, Madurai. Sir has completed his PhD from Madurai Kamraj University, from USA, that is MIT University. Sir has visited Japan, Israel, Spain for his research program. At MIT, Sir has designed and developed a new indigenous experiment to measure the magneto-thermomechanical properties of smart polymer composite materials. He has received the prestigious JSPS Fellowship from Japan and Research Award by UGC New Delhi. Sir has been recognized as the Fellow of Tamil Nadu Academy of Sciences. Under his guidance, 17 students got PhD degree. Sir has completed 11 major projects funded by DST, CSIR, ISRO, DRDO, UGC, DAE, CSR, Indore and Mumbai. Sir has established a smart material research lab for his credit. He has published 105 research papers in his period with high impact factor journals. Presented research fundings in 150 international and national conferences. Sir has organized 25 international and national conferences as well as workshops, including INSA, AI, MHRD, TEQIP, ICASM, MAGMA, QEEE. Sir has delivered 45 innovative talks in international and national conferences, including IITs, NITs, NBL, DMRL, SICRI, and also 135 guest lectures in schools and colleges. His 5 video lectures, that is bilingual, prepared by the Tamil Nadu state government, have been sent to all engineering colleges and schools in the state and also available in YouTube. To his credit, Sir has completed 6 online courses in MOOC. Sir is the life member in the professional societies like MSI, ISSS, ISTE, IPA, and MRS. Sir is promoting the beauty of ancient Indian science and engineering practices by conducting workshops for teachers and students. Sir has acted as a resource person in the workshops conducted by Teachers Recruitment Board, and the Tamil Nadu School New Curriculum Development. Sir has guided our colleague Dr. Geeta. We have such an eminent scientist as our resource person in our midst. Sir has accepted our invitation amongst his busy schedule. Now, Sir will give lecture on magnetic smart materials. Now I call upon our resource person, Dr. Manikyam Mahendran.
Sir, just I interrupt you. Just before we go into the main talk, let me now request the principal of our college to speak a few words as presidential address.
Extremely sorry to join by little later. Anyway, because of the internet connection, I'm delayed. Okay, I'm very proud to be here as a principal of the Nesamani Memorial Christian College, Marthandam, for the international webinar entitled on magnetic smart material. I'm really very happy and congratulate the organizers, the Department of Physics and Research Center, as in association with our college IQAC, especially the head of the department, Dr. Sheila Christie, the IQAC coordinator, Professor T.B. Thomas, the convener of this today's program, that is Dr. Rachel J. Gita, the co-convener, Dr. A.S. Jabamalam. I heartfully welcome our today's guest speaker, Dr. M. Mahendran, Professor and Head of Department of Physics at Tyagarajar College of Engineering, Madurai. I think for the today's webinar, more than 220 participants across the country joined here in order to enrich their knowledge regarding the magnetic smart material. Today, the most promising technologies for lifetime efficiency and improved reality include the use of smart materials and structures. Material science is the study of the properties of solid materials and how these properties are determined by material composition and structure. Smart or intelligent materials are they can significantly alter one or more of their inherent properties owing to the applications on external stimuli in a controlled fashion. The several external stimulus to which the smart materials are sensitive are temperature, pressure, moisture, electric field, magnetic field, etc. Magnetic smart materials are also called rheological materials. These are in liquid phase which can change state instantly through the application of an electric or magnetic fields. These fluids may find applications in brakes or shock absorbers and dampers for vehicle seats. Many more applications from the smart materials, especially from the magnetic smart materials, such as fiber optics, sensor, then biomedicines, drug delivery system, organ replacement, robotics, aircrafts, smart fabrics, smart classes, and so on. So today this webinar definitely enriched the particular field, that is magnetic smart material. All of us will be benefited, especially those who belong to the faculty of the physics. Both research scholars and staff and students will be enlightened with the new ideas of the magnetic smart materials. So in this morning, I once again welcome all the participants and resource persons for this wonderful webinar arranged by the Department of Research Department of Physics in association with the IQAC of our college. I thank one and all. Thank you, sir.
Thank you, sir. Principal, sir, thank you so much.
Thank you, sir. Thank you.
Thank you so much, dear Principal, for the nice words as presidential address. Now we move ahead with today's program. So let me now once again invite Dr. M. Mahendran, Professor and Head of Department of Physics of Tyagarajar College of Engineering, Madurai, to continue with the presentation on magnetic smart materials.
Thank you, sir. Thank you, IQAC coordinator, sir. Thank you very much for a nice introduction about this workshop and about your college. Of course, I visited a college several times. Can you? Is my audio? Hello.
You're audible, sir, but I think you have got a small network issue there.
Can you hear me, sir?
Yeah, I can hear you, but the voice is breaking.
Okay, okay. Let me check my again. Yeah, of course. My video is full. Okay, let
Yeah,
me.
it's fine. It's fine now. It's fine now. Go ahead.
So I had to bring my laptop close to me. Okay, fine. I think it is okay now. Is it okay?
Yes, yes, sir. Yes, sir. Fine, fine.
Geeta, madam? Is
Yes,
it
sir. Yes, sir. Okay. Now it's okay.
okay? Bala, sir? Sona, Bala, sir? Can you hear me? So most of the participants are known to me, of course. I saw that list. It is a very huge list, right? So great, Geeta. It is a very nice arrangement. Of course, Pushpanathan is there. And my
Thank you, sir.
students like Geeta and Bala and Vinolin and most of the fine. Anyway.
Good morning, sir. I am Ramesh, Near Memory College.
Oh, Ramesh is also there.
Okay, sir.
Really great, Ramesh. Nice.
Okay, sir.
Okay.
Okay, thank you.
Sir, Geeta, shall I share my screen? Yeah, of course. Let me share my screen.
Yes, sir. Yes, sir. You can share.
Is it visible? Can you see my screen?
Yes, yes, yes.
Okay, fine. Okay, that's good. Okay. What about my slides? Is it okay? Okay, I have to do this. Okay. Oh, I have to close this. Fine. Okay. Yeah, all right. Geeta, can you see me? Can you hear my audio?
Yes, yes, yes,
Yes,
sir.
sir.
Okay, audio is okay. That slide, what about my slides? It's okay? Is it visible clearly?
Yes, yes, visible. Madurai.
Thank you so much, sir. I'd like to thank the principal NMCC and IJKOC coordinator and head of department, Dr. Sheila, and my own PhD student and faculty in NMCC, Dr. Geeta. And of course, I had to thank, special thanks to Dr. Aruldas for his nice introduction about my academic profile. And I should again thank the principal for his beautiful overview on the smart materials. Really, it was wonderful to to see his overview on smart materials. Such a good overview. Fine, thank you so much. Anyway, so Madurai is popular for the Sungadichari, and of course Madurai is popular for in fact not for Nayandara, but it is popular for jasmine export. That means Madurai has got we have got our own geographical induction values, like for Sungadichari and jasmine. Of course, Madurai is popular for for making this kottu paratha. Okay, fine. This is out of the syllabus. Okay, fine. Okay, right? Yeah, right. So my top of today's talk is on. I'll be talking on the magnetic smart materials. Actually, so basically, this new kind of smart materials. Again, it is recently discovered new materials like what you people are talking about, nanomaterial. Actually, nanomaterial is one of the class of smart materials, and magnetic materials, nanomaterial, biomaterial, composite material. So all these materials can be combined to have a new material called the magnetic smart materials. So of course, obviously, the principal has rightly said that this material has a wide variety of applications, right from the home appliances to the space applications. Because he's right, absolutely right, that these materials are being used in the space applications to to launch some specific antenna or in which the kind of actuators called the nickel ionic actuators and IQAC coordinates, sir, can you please mute all the participants? Yeah, okay, fine. Okay, right. Okay, right. So therefore, this material has huge applications in the day-to-day life, and I told you that right from the space applications to the home appliances. So in particular, if we take our passenger car, say for example, a car, or in particular the automobile industry, in particular the passenger car, in which almost 99% of the materials being used in the construction of or in the designing of the passenger car is your smart materials. Right from, the shaping mineral alloys, smart polymer composite, a macrorheological fluid, electrorheological fluid. So most of the materials or smart materials are being used in the construction of passenger car. Okay. So now the question is, what is so special about magnetic smart material than the conventional material is that the magnetic material can be used as a beautiful actuator. See, actuator is what I mean is, it is basically a vibrator which makes up and down action. So say when an external field is applied, say for example, you can apply magnetic field to some device. As a result, the device can make up and down action like this. This up and down action is what is known as the actuator action. Therefore, this material can be used as a best actuator. To some extent, this material can be used as a best sensor also. Okay, right? Why? What is the difference? What is the speciality? What is the superiority of this material is that, this material is the vibrating action is, which takes place at very fast rate than comparing it, what is called the conventional smart materials like nickel, titanium. This material, nickel, manganese, gallium, of course, this is a magnetic smart material. This is much faster than the conventional material. That is why our research is focused on the smart materials. Actually, I have initiated this research on smart materials at MIT USA under the guidance of Professor Robert Hanley. So really. So this this picture shows just just for fun. Anyway, this is one way of preparing the material science. You can prepare your own new materials in the by heating the material to high temperature in the furnace, this and that, and finally you'll get a product like that. So preparing the material science and new materials like preparing a sambar or chutney or whatever, right? So see the beautiful prepare your own new materials in your department kitchen. Fine, right? Okay, right. So I'll be talking on I'll give a small introduction about smart materials, and I'll be focusing on ferromagnetic shaped mineral alloys, and I'll emphasize on what are the basic physics principles behind in the development of new ferromagnetic shaped mineral alloys, and how these ferromagnetic shaped mineral alloys respond to the application of magnetic field, and how the strain produced in the ferromagnetic shaped mineral alloy, as a result, this can be used as an actuator. But the question here is, since this ferromagnetic shaped mineral alloy is brittle nature, as a result, it will break easily. So what we did is, we just used the nickel manganese gallium so as to have a polymer composites. Because it is a composite, right? A matrix will form, the material will form the matrix. As a result, it is easy to, you can produce a ductile material. So the nickel manganese gallium alloy has been used to make our own polymer composite. Of course, fine, all these are newly discovered areas in material science. So for the first maybe 30 or 40 minutes, I'll be talking on the smart materials, and the rest of the 5 or 10 minutes, I'll be talking on the out of syllabus content like nano-processing, nanotechnology, and how a journey travels from nano, a journey of nano from doser to device. So very simple, just for fun, but it is very serious science behind in the development of nano-processing and nanotechnology. A serious science is there. I'll let you know. Okay. So for this out of syllabus content, I'll take only 5 minutes or less than 10 minutes. Fine. Okay. Yeah, of course, obviously everybody knows that. Say there is a beautiful book, you must be knowing that, Material Science and Engineering by William Callister. It is like, a very beautiful book. It is like a Bible or, or whatever the book that you're talking about is a very beautiful and a wonderful book to know the basics or the fundamentals of material science. Please go through this book, William Callister. So material science is basically, material science is basically, the interdisciplinary area comprising engineering, physics, chemistry, biology, and all this, right? Why? Because material science deals with the properties of atoms or the atomic arrangements. As a result, you can have your own properties. Whereas all these properties will be given to the engineers, and engineers, what is called the materials engineer. They'll be in a position to analyze or design their own components called the engineering components. Therefore, the role of material scientist is to discover a new material, and for this new material, you will have new properties like, you can design your own, you can determine what is called the thermal property, magnetic property, mechanical property, like, stress and strain. All these properties can be defined or determined, and outcome, all these properties will be given to the engineer, and the engineer will be in a position to design their own components, what is called engineering components. And finally, all these components used to analyze, used to design a new product. That new product may be your car. So therefore, what I'm trying to say is that to have a new product, to get a new, the society will get a new product only. It is a teamwork, kind of teamwork, right? So material scientists and materials engineering. So these two teams will sit together and work together to give a product like a passenger car, a smartphone, or the television or laptop. And finally, all these products will come to the society, and we are using it. Okay, fine. Anyway, this is material. So therefore, what I'm trying to say is that material science, without the material science, he cannot think of engineering. He cannot imagine what is engineering. If there is no engineering, there is no life. Of course, that is true, right? Yeah. So just I'll give introduction again. How to prepare material? There are 4 steps are involved in preparing the materials. As you all know that most of the participants, I just saw the list. Most of the participants are doctor, right? And most of the participants are PhD students. I heard from Kita. Fine, right? Anyway, this is again the slides that which gives you how to prepare a material. Maybe if I heard from Gita again, some students, MSc students are sitting here in the, webinar, right? So there are 4 steps are involved in the preparation of the materials, right? The first, processing. So processing, what I mean is like, the synthesis of material, right? You have to pick some, 5% of nickel and 10% from iron on this. All this will be put in a crucible, and they'll put it in a furnace, and you'll get a new material. And you'll analyze all the basic structures of us. They you will analyze the crystal structure, you will analyze, a phase transformation, this and that, right? So that process is called synthesis. So next, what you'll do is that you'll analyze the microstructure. Just look at the vegetables, right? Where different colors of atoms are, looks like, arranged, right? And the surface of the material, the atoms will be arranged like this, right? Like tomato is one group of atoms, and onion is another group of atom, and ladyfinger, right? So this is a surface atom. So if you look at your new material that you prepared from your furnace, you have to analyze the microstructure of the material using your SEM and TEM. And based on the atomic arrangements, how the atoms are, whether atoms are closely packed or loosely packed, depends on the arrangement, or depends on the intensity of the atomic. Define your own properties, right? So the properties, what I mean, it is like a sambar, right? Whether it is onion sambar or vengaya sambar or takali sambar or murungaka sambar, whatever, right? You can define various properties like thermal property, magnetic property, depends on what is called the atomic arrangements. And finally, the product, the third product, finally product, whether it is good to eat or like Rajkran, whether it is taste or delicious or something like that. So finally, the engineer. So all these properties will be given to engineer. Engineer will be in a position to analyze what is called the performance of the new material. Say for example, product. Just look at the sickle, right? This is Arwa, Vetarwal, right? So that is the product. And once all these process, these 4 steps are have completed, what you can do is you can analyze the performance of the product, right? So whether performance, what I mean is like the reliability and the efficiency, all this will be checked by the engineer, not by the physicist. Anyway, that is why these 4 steps are involved in the preparation of the material is important. Okay, fine, good, right. We'll just go to the topic. Anyway, I think I have to change this. Okay. Let me. It's not moving. Okay, let me keep this like this. Okay. Yeah. Okay, right. So this is as usual, this is a very simple topic, simple, of course, the topic is a bit complicated, but the definition is very simple and straightforward that basically this is a smart material. Basically, so just look at the phrase smart, right? A material which changes its characteristics and properties according to the atmospheric conditions. Whenever there is a change in the atmosphere, what happens is, what will happen to the material is that all the properties, all the characteristics of the materials will also be changed. That is why it is called a smart, right? Maybe I can say that a smart material, the colloquial example for smart materials are politicians. So why? Because the material which changes its properties, which can change its properties and characteristics according to the atmospheric conditions. See, if the politician is used to switch over from party to party, and he is accustomed with a new party, right? So material, smart materials like that. Whenever there is a change in the atmosphere, the material property will also be changed. Whenever there is atmosphere, environmental condition, if there is a change in the environmental conditions, the material property will also be changed. So that is why the material is defined as, they have their own nervous system. Why? Because nervous system, right, which has the ability to both sense and communicate with the outside intelligence. That means this is a specially discovered material because of the nervous systems, because this one nervous system is not present in any other material. And this material, the special feature of this material is that this is a single material which has 3 different functions, which can be used for 3 different functions. Say, for example, the smart material has sensing ability, actuation ability, and processing control. But just you can ask a question that what is the difference between the smart material and the normal material? Normal material is that in normal material, say for example, you take cobalt, or you take some aluminum, right? Aluminum is a single material, or cobalt is a single material. Okay? That material can be used, the single material can be used for making a single function. On the other hand, smart material is one. Again, this is a single material, but this can be used for 3 different functions, right? 3 different functions. So that is the difference between these two. Why? Because they possess the sensing ability, actuation capability, and processing capability. See, these 3 are interlinked. That means smart materials can be generated using sensor, actuator, and of course, again, the another example for smart materials are biomaterial, right? Like I used to give this example. See, most of the participants are known to me and they are familiar with this slide, I guess, right? But still, I used to give this example. There's a beautiful example that, see, when mosquito is sitting over here, what happens is that, see, the mosquito, it communicates through this vein system, because there's a sensor. Skin is a sensor. The communication is sent through this vein. As a result, what happens? It reaches the brain, and brain tells the hand that a mosquito is sitting on your hand. Then brain orders the same hand to strike it, to hit it. So what happens is to hit it? So this is an actuator, skin is a sensor, and these 2 is called the processor. Okay, right. Anyway, so therefore these materials are classified basically. The smart materials are classified into all these. You can classify these 2 materials into various types like piezo, electrostatic material, and of course macrodestructive materials like iron. Gallium is one of the important macrodestructive materials which is being used to make actuators. Yeah, of course it is being used in the market. It is one of the rare earth based materials, macrodestructive materials, right? It is being used. Mostly Chinese, they are using this macrodestructive materials to produce more actuation capability, because China, so in China, so huge rare earth materials are available, of course. Yeah, the world number 1 rare, of course, the huge quantity of rare earth materials are available in China, of course. And of course, our research is focused on ferromagnetic sheet mineral alloy and to some extent thin film. And of course, these are some of the students that who got a PhD in ferromagnetic sheet metal alloy, and including Dr. Geeta and Dr. Puspanathan, who is there, who is in he is one of the participants now. And anyway, macroneurological fluids. We are doing research on macroneurological fluid. Of course, 3 students are completed, and we are doing research on theoretical computation material science. Anyway, 3 students are completed, and now Dr. Sinitra is in doing postdoc abroad. And currently, 4 of my students are doing full time in this. Right now, they are going to submit their thesis. Okay. Anyway, they are also doing research on smart materials. Anyway, these are the classification of the various types of smart materials. Okay. Fine. So our research is focused on shape memory alloy, in particular ferromagnetic shape memory alloy. So let me explain what is a shape memory alloy. Basically, it is an alloy which memorizes its original shape even after severe deformation is called shape memory alloy. That means a material memorizes its original shape. Say, for example, you take or whatever, say the strings that are using that are being used in the construction industry, right? Like what they call the kattukambi, right? Or you think of a laboratory meter scale, right? When you try to bend your laboratory meter scale, what will happen is at one stage the meter scale will break, right? On the other hand, if the same meter scale is made of what is called the shape memory alloy, what happens is shape memory alloy, what happens is it will not break. On the other hand, even whatever the position you can squeeze it, or whatever the position you can deform it, but once the material is heated, what happens is it comes back to the original shape. That is what is called the memory material. Why? Because it produces, that means the transition between 2 states or 2 phases is taking place in shape memory alloy. One is the martensite phase, which is occurred at low temperature, and the austenite phase, which can be obtained at the high temperature. So the temperature from the room temperature, it goes to high temperature, comes back, goes up, comes back, goes up. So similarly, the cycle goes down. So one of the popularly known shape memory alloy and conventionally used, of course, this shape memory alloy is being used in the market. Hugely, they are used in the market, nickel titanium. So in which the shape memory alloy was effectively observed. Because in which, of course, our physics Hooke's law is being used. And this material can also be called, say, for example, just listen to this video. Yeah. So that is why this material is called the muscle material. Just look at Vadivel, right? It's a muscle material. Why it is called the muscle material is that, say, when a severe deformed force is applied, when you try to press your hand, what happens is a cavity, a small hole will be formed, right? A cavity, right? Or like a pallam, right? It will form. When you remove hand, what happens is this cavity will be removed automatically. That is why this material can also be called the muscle material. Or this material, shape memory material, can also be called the cyclic material, what I can say. Okay, so what is the basic physics began in it, right? So the basic physics began in this material is, of course, we are all familiar with the solid state physics kitten, that slipping mechanism is occur. Slipping mechanism is occur in ordinary crystal or ordinary material, in which the atoms are moving one by one. On the other hand, in the shape memory alloy or the smart material, twinning mechanism has occurred. That means the atoms are moving as a cooperative filament. The first one, slipping mechanism, is what is called the civil transformation. And the second one, twinning mechanism, or the twinning mechanism is occurred, which is called the military transformation. The civil is atoms are moving one by one. On the other hand, military transformation, atoms are moving as a whole, right? That is why this. So this is the major difference between the normal crystal and the smart materials based crystal. Okay? Yeah, of course, these are the basic classifications that I'll be talking on the actuator based material one. So for the actuator-based material, you can apply heat to, the nickel titanium material. You can apply electric field to PZT. Yeah, when a magnetic field is applied to nickel manganese gallium, what happens is, so the material starts actuating. And just look at the animation. Of course, I took this animation from the website that, see, in normal shaped mineral alloy, nickel titanium, in which the temperature is applied, as a result, the shape or the size, shape, everything is changed. On the other hand, just come to my magnetic materials, magnetic smart materials. What happens is, in rare earth material, this is the first one. The middle animation shows that it is a terphenol. Of course, see this one, the terphenol D. This is one of the rare earth material in which the magnetic field is applied. When a magnetic field is applied, what happens is, only the arrow represents conventionally. Of course, this is called variant, but the colloquial name for this variant is that we are familiar with that name, what is called domain. In the domain, the arrow represents magnetic moment, but here what we call the variant, right? In smart material, the arrow or the whole area is called variant, right? So when a magnetic field is applied, the magnetic moment is rotating only inside the domain. On the other hand, in ferromagnetic sheet mineral alloy, just look at the animation, it is moving, the boundaries are moving. As a result, it can go up, comes down, go up, comes down. So when a magnetic field is applied, the boundaries are moving, it can go up. So as a result, it goes, say the actuator starts like this. When a magnetic field is removed, it comes down. When a magnetic field is applied, goes up, comes down, goes up, comes down. So that is the beauty of this ferromagnetic sheet mineral alloy. As a result, all these materials can be used for making your own actuator and sensor. Okay, fine. Yeah, what is the difference? What is so special about the ferromagnetic sheet mineral alloy is that, the only difference is, see, you can have as many as number of possible alloys to work it as actuator or sensor. But the question here is that which alloy, you have some n number of alloys, you have some 10 or 15 alloys, which alloy possesses maximum strain so as to use it as actuator. Only when the alloy possesses maximum strain, that alloy can be can work as a best suitable candidate actuator. For example, nickel titanium, of course, the maximum strain produced in nickel titanium is 10%, as of now 10%. But just look at the x-axis in which the frequency is smaller, just 10 hertz. On the other hand, if you look at the terphenol D, and just in the diagram, terphenol D is there. Here in the terphenol D, and the frequency response is larger, but just look at that terphenol, basically it is a rare earth material. That material has the ability to produce only 0.2% strain. Though that process, I say, the response of terphenol is very, very high, but the percentage, the amount of strain produced in this material is very small. So you cannot use it for a large number of applications. So therefore, our objective was to look into a new material which has the ability to produce, which has the ability to possess both maximum strain and fast frequency response, which is one of the important materials, nickel manganese gallium. But nickel manganese gallium is highly, of course, the response, it is high, huge responses there, large amount of strain can be produced, response, non-contact with the material because you're applying only the, magnetic field, and the twin boundary can easily move. So in spite of all these advantages, the material has one disadvantage, that it is highly brittle and easily break. So when you do this action like this, and it will easily break. So that is a major drawback. That is why this material, nickel manganese gallium, is miserably failed and it is not being used as of now. But this material has been mixed with iron and some other antimony tin, so as to have, what is called this. So as to use it as a spintronic device. Yeah, this is basically half Husserl alloy. Husserl alloy, right? HEUSE alloy. So that is because of the disadvantage of this material. Okay. Yeah, basically this is, see, listen, this is all this magnetic material. Okay, this is, you're most familiar with this magnetic material, right? Yeah, don't worry. Yeah, I told you know that how to prepare. Of course, you have prepared your alloy, what is called the nickel, manganese, gallium, ferromagnetic sheet metal alloy. Now the question here is how to confirm it, whether it is the alloy that you produced is really a ferromagnetic sheet metal alloy or something like that. Right? See, I just see Aro Polar. I used to prepare some sambar, right? You could try pani now make sambar try pano. So that sambar you have to taste test whether the sambar is, if not delicious, at least that has to be checked. The taste of the sambar or the ingredients of sambar will be checked by the master chef Amma, right? Similarly here, preparation, I mean, you can easily prepare the new ferromagnetic sheet metal alloy. It is not a big deal, right? It is easy to prepare the alloy. Anybody can prepare an alloy, but the question here is whether it is a ferromagnetic sheet metal alloy or not, that should be checked, for which that new alloy must satisfy all these 4 conditions. Obviously, it is a ferromagnetic sheet metal alloy. What will happen? See, if it is a ferromagnetic material, it has to produce, you can use a hysteresis loop to change, I mean, to show, I mean, to draw your hysteresis curve. In the hysteresis curve, you can see the saturation of magnetization. Once if you have a saturation of magnetization, obviously the first condition is satisfied that the alloy that you prepared is ferromagnetic nature. Fine, confirmed it. And condition number 2, you have to analyze, obviously you have to analyze the microstructure using your XRD, SEM, this and that, for which you can use lattice parameters, whether what is the structure possessed by this material, right? Whether it is tetragonal material or orthorhombic structure. If it is an orthorhombic structure, because the C is less than A, which has C is greater than A, what happens is it has 2 structure. One is tetragonal, another one is orthorhombic. At orthorhombic, the amount of strain produced is large. Fine, that should satisfy. And another important condition is, see, when a magnetic field is mechanical stress is applied, and simultaneously apply a magnetic field, what happens is this magnetic field should overcome the mechanical stress. It has to possess that ability that can be checked using some the universal testing machine, this and that. And the 4th important condition, of course, this is very, very important condition, the material should possess high magnetocrystalline anisotropy, simply the magnetic energy. It should possess high magnetic energy, huge amount of magnetic energy should be there, so that it is easier to move the atoms. I mean, atoms present in the plane. Say, for example, we heard about black wall. Of course, yeah, I studied about black wall, or what is called, in the black wall, we studied about the soft magnetization axis, soft magnetic material and the hard magnetic material, or easy magnetization axis, hard magnetization axis. Yeah, so all this depends on the atomic arrangements. So the 4th condition is important, that the material, only if the material possesses huge amount of magnetic energy, the twin boundary can easily move. As a result, you can have your actuation. I mean, the material can go up and down, and so as to act as an actuator. Yeah, I told her, right? Just now I told her that is a twin boundary, right? See, you have this the pair of twins are there. Twin, what I mean is M1, M2, or what is called colloquially ferromagnetic. See, basically it is a ferromagnetic material. Ferromagnetic material, large number of domains are present. Domain is the smallest area in which the magnetic ones are oriented in a particular direction. Similarly here, this ferromagnetic sheet metal alloy. Just assume that we have 2 domains, one is M2 and the M1. For this domain, you can apply the magnetic field. What happens is, if the magnetocrystalline anisotropy is very small, what happens is these 2 domains will be flipped up. See, it will not move, it will be flipped up. On the other hand, if the alloy that you prepare possesses large magnetocrystalline anisotropy, what happens is it will not flip up and it will move like this. It will act like this, right? So that is why it should, the 4th condition I told you that it should possess strong magnetic anisotropy. Yeah, now, right, this is my structure, right? Just look at the left side. This microstructure is there. And microstructure of this material, you can apply mechanical stress. Just look at the direction of the mechanical stress. And I told you, there are n number of twin boundaries are there. And this is the direction they applied mechanical stress. And this is the direction of the magnetic field. What happens is mechanical stress is going down, simultaneously applying magnetic field perpendicular to the direction of the mechanical stress. What happens is, just look at this is the direction and this is the direction. Now, what happens is, you see, mechanical stress and yeah, when a mechanical stress is applied, when you keep on applying this, all this magnetic moments, you see V1, V2 are the variance, right? And one stage, when you keep on applying the magnetic field, just look at the mechanical stress. So if this is the direction, I told you that the third condition to confirm a ferromagnetic law is that it should be easily twinned via the external stress. So this is my external stress. When a magnetic field, it should overcome, then only you'll be in a position to produce more amount of strain as a result. Just look at this. In the material, finally, you'll get your stress sigma and you'll get strain epsilon. Yeah, this is nickel, manganese, gallium, ferromagnetic law. Okay, fine. Finally, yeah, you see this one. This is a look at this video. I don't know whether you're able to see my video or not. Just look at all the twin boundaries are moving, right? Just look at this one and another video, and it makes just minute. Here minutely watch that it makes up and down action. This is Professor Roberto Handley. He is one of the. I told you in the very first slide that he is one of the inventors of smart materials. Of course, I did my postdoc under his guidance. Really, I had to thank him, and I dedicate this lecture in the fond memory of Professor Robert Handley. He is no more now. Fine. Let me took my a chart. Anita, okay. Oh. Okay. Yeah. Okay. Fine. Right. Yeah, these are the various types of actuated materials. Say you can have, shape memory polymer, piezo ceramic. Of course, basically the piezo ceramic material is being used in, the lighter, right? In the kitchen gas lighter, right? When you press this, So this is, you're applying mechanical stress to the PECT material. Actually, basically, a PECT material is being used in your gas lighter, right? When you press this like this, it produces electric charge. As a result, it gives you, the mechanical energy is converted into electrical energy in a simple lighter, right? So these are the various types of materials that are being used to make actuators, but the actuator depends on the amount of strain, and the amount of strain depends on the application in which you are going to use for your own purpose. See, not all the actuators, not all the materials will be used for making a single actuator. Depends on the application, depends on the use. The materials, the smart materials will be used to make their own actuators, right? Yeah, I told you that. Okay, anyway, this is time. Okay, now anyway, so I just talked about the nickel manganese development of nickel manganese gallium actuator, ferromagnetic law to use it as an actuator, but it has brittle nature. What it did is just made some powder form. Of course, Geeta, our madam, Dr. Geeta, did research on this area, and we powdered such, and we have used it to make polymer composite. Of course, it will take much time and almost time now. We did some research. Of course, this is a beautiful work, and we carried out it and did all this to make the polymer composite and confirm it finally. Yeah, this is a experience setup that we have in a laboratory to produce the smart materials and to check to determine the various properties with a special emphasis on the mechanical properties. We have our own setup. Of course, this lab has equipped with all projects funded by DST, CSR, and UGC. Fine. Okay. Yeah, of course, I did some research how the energy is suppressed and how the nickel manganese gallium is acted as the energy suppressor. Okay, that will take much time. Maybe if time permits, I'll I'll talk to the NMC students later once the pandemic situation is normal. Okay. Yeah. Right. Yeah. Of course, we did some research on because again composite. Actually, our objective was to make an actuator. So miserably failed. Then it went for just we tried preparing the composite. Again, it has failed. And now we are trying to make this ferromagnetic thin film. Of course, Dr. Vinod Kumar did wonderful research. Of course, it works well because all these properties, of course, he has completed and still he is doing research in ferromagnetic sheet metal, a thin film. Of course, it works well. We can make an actuator, but peeling of the actuator is a bit difficult. Okay. Of course, it is confirmed that all the results are encouraging. The DSC, SEM and mechanical properties. In fact, all the magnetic properties, all the results are good. And we are doing research. Currently, we are doing research on ferromagnetic sheet metal, thin film also. Okay, fine. Yeah, we did some research on temperature and okay. Okay, my dear students, my dear participants, not students, of course, my colleagues and students. So please, youngsters, please avoid plagiarism and it is a serious issue these days. Okay, right. And don't worry about the rejection of the papers, right? At first, this is Professor, Herbert Humer. Of course, he's a Nobel laureate. His first paper was rejected, right? But he has carried out all the correction and submitted to some journals. And the mobile phone that they're using, the smartphone that they're using is in which semiconductor heterostretcher is being used in high-speed optoelectronic devices, right? This is one of the high-speed in which the bandwidth is large, right, for being used in a broadband communication. So though his paper was initially rejected, but the same paper was carried out and he filed the patent and used it. And yes, of course, he is one of the Nobel laureates. His first paper was rejected, but that material is being used in the smartphone. That is a beauty. So my dear youngsters, my dear young guys, don't worry about the rejection of the papers. So the beauty is there are totally 8 rejected papers that won the Nobel Prize. So one day, of course, my papers have been mostly at first sight, most of the papers have been rejected. Hope I think any of my students will get Nobel Prize which can be used as a damping device. To reduce large amount of sound energy or mechanical energy, or to arrest mechanical energy. As a result, this can be used in automotive industry. That is why I told in the very first slide that this material, 99% of the smart material is being used in making the passenger car, right? Fine, good. So fine, good. So let me take just 5 minutes to brief about the ancient Indian science. Geeta, with your permission, shall I take 5 more minutes? Geeta, Dr.
Okay, sir. Okay, sir. Yes, sir. Okay. You can take.
Okay, fine. So this is very interesting that I'll be very happy in sharing or in talking about. Of course, I told you yesterday, Geeta told me that most of the participants are from Kerala. But still, I think understand what is a Tamil. Okay, right. Anyway, I'll be talking on the nanoprotosome nanotechnology, how the nanotechnology has been originated. The nanotechnology has been originated from the Department of Kitchen, that too, Thai Margal, when you try to make your own, dosa or idli mavu, you have to grind it to a smaller scale. What happens is the rice particle, it becomes a smaller. You can keep on grinding in which physics principles used, the centripetal force and centrifugal forces. And this is what is called Tirkai, and you can rotate it and your centrifugal force is used. Again, this is Ammi. Again, you can grind the particle to small level. See, that is a basic, right? Grinding the particle to small level leads to nanomaterial. For example, what is nanomaterial? Say, for example, just look at my palm. You can keep one apple here. This is the surface area. You can keep one apple here. What happens is that one apple, assume that one apple is an atom. That single atom is doing some work. Remove that atom. Now keep this here in the same surface. Keep 4 nellika, just keep it on, right? So the single atom, whatever the work did by the single atom, now the single atom work is doing by 4 different atoms, nellika, right? Now remove all 4 nellika, right? Now what you can do is just keep in the same surface, keep like in a mustard, right? Kadugu, for example. So you can keep some in the same surface area palm, you can keep some 100 கடுகு 100 கடுகு அதில் வைக்கலாம். ஒரு ஆப்பிள் ஆட்டம் பண்ண வேலை. Now the 100 atoms are doing. Just think of the efficiency. As a result, simultaneously the size is also reduced. So now that is why the nanotechnology has been originated from our department kitchen. That means that too from, I guess from India, because we used to make prepare idli and dosa, for which we have to prepare our own idli or dosa maavu, for which we have to grind the particle to smaller level. That leads to nanotechnology, I'm damn sure. Okay. Yeah, just listen, right? In தமிழர்கள் எவ்வளவு அருமையா அதுக்கு ஒரு அருமையா ஒரு விளக்கம் கொடுத்திருக்காங்க பாருங்க. nanotechnology, how the particle size is reduced to smaller level. அல் means சில், துண்டு, குட்டி குட்டியா நறுக்கிறது. அழுகுதுன்னா ஸ்லைஸ் பண்றது, கொஞ்சம் கொஞ்சமா ஸ்லைஸ் அப்படியே பண்ணிட்டு வருது. அறுப்பம் சிறியது, நுண்ணியது, அதெல்லாம் அரிசி சொல்லுவோம். அரிசி 2-3 உடைஞ்சா அது குருணைன்னுவோம். So we used to talk when use this word nice. Nice is actually நொயின்னு பேசாதன்னு சொல்றோம். So குருணை is a macro and நொய் is a micro. நொயின்னு பேசிக்கிட்டே இருக்கான்னு சொல்றோம். That நொய் means in English it is nice. So that is why இந்த தமிழர்கள்ட்ட இருந்துதான் nanotechnology. Of course, I feel proud that the nanotechnology, I guess nanotechnology has been originated from, Tamil Nadu or something like that. I don't know, because தமிழர்களே எல்லாத்தையும் முன்னோடிகளா இருக்காங்க. ஒருவேளை அதுவும் இருந்திருக்கலாமோ அப்படின்னு சொல்றேன். So just look at the definition of nanotechnology. Okay, fine. Yeah, and just look at the results.
நல்ல வாசமா இருக்கு, அவ்வளவு வாசம்.
Sorry. Okay. So again, I can and even in Ahananuru, how to make a nanotechnology, a nanomaterial, it has been proved. And of course, even in Sindhu Samavaliல உரல் உலக்கையை பத்தி நிறைய பேசியிருக்காங்க. மீன்ஸ் பாறையில கூட வச்சு ஒரு பார்ட்டிகல்ஸ் அப்படியே கிரைண்ட் பண்ணிக்கிட்டே இருந்தோம்னா you'll get smaller size. That leads to nanomaterial. That leads to nanotechnology. So okay, fine. Just look at the size of the nanomaterial, right? So first, bigger size macroparticle is reduced to the microparticle like nellika or milagu. Then again the nanomaterial மிக சிறியது, கடுகு, கசகசா. So this is a way you can reduce the size of the particle, which leads to nanotechnology and whatever. And the nanomaterial used to make size shrinkage device. Just think of size shrinkage device. What I mean is, just think of the what is called your pen drive, USB pen drive, right? Yeah, just look at the position of the ancient devices, right? The artoral ammikalla eppadi kadakkum, but at least they're using it. Yeah, what I'm trying to say is just to make your nanomaterial. Of course, I have this instrument, ball milling, which costs some 10 lakhs, right? This ball mill, artoral ammikal enna vela paathucho, the same work adha appadiye da indha ball mill panikiட்டு இருக்கு, right? So what is the use of it? So just தமிழர்கள் ஒரு 500 ரூபாய் உரல்ல நானோமெட்டீரியல் ப்ரிப்பேர் பண்றாங்க. But this instrument which uses same principles that have been used in traditional mill, art uralla, like centripetal force and centrifugal force, but here it is being used. Okay, fine. Yeah, of course, as you know that Feynman is the forefather or the father of nanotechnology. They used to say that because he used to tell that there is a plenty at the bottom of the room, because obviously. But the word nanotechnology has been coined by Professor Nori Taniguchi in 1974. Just think it out. The word nanotechnology has been popular. Of course, let us say the age of nanotechnology is roughly over 40 years, right? 40 வருஷம் தான் இருக்கு. ஆனா தமிழர்கள் நானோ டெக்னாலஜி அப்ப 3000 வருஷத்துக்கு முன்னாடி அகநானூர்லயே தொல்காப்பியத்திலே சொல்லியிருக்காங்க நானோ டெக்னாலஜி பத்தி அப்படின்னு தான் சொல்லணும். பட் we are not coined a new technical word nanotech, but we use the technology, use the grind the material, right? So that is why we used to say தமிழர்கள் தான் நானோ டெக்னாலஜியோட forefathers ன்னு சொல்லலாம் அப்படின்றது என்னோட கருத்து. Okay. Yeah, this is important. My dear youngsters, you should be very careful, right, in using your cosmetics, right? So maybe I love to look like Ajit by using all cosmetics, this and that. My girls may be interested in looking like this actress, but the outcome is, this is the outcome, right? Be careful in using the cosmetics, my dear youngsters. So why? Because see, in all these cosmetics, zinc and titanium at nanoscale is being used, which are hazardous to health. Okay, please be aware. See, if the cosmetics, if really the cosmetics that you're seeing in the television advertisement, if really it works well, why not? See, Rajinikanth, our young sopa well, our tailor the casa, Narea, our the cosmetics, so it is true. It is not true, right? They're cheating us. So avoid using cosmetics. Say, Rajinikanth, so think of, right? He has a huge money, this Sarana store owner, right? So what I'm trying to say is all these cosmetics are made of nanomaterials. And in the nanomaterial cosmetics, they are useful. They are metal hazardous. They're not good for health. My dear youngsters, please avoid using cosmetics. Okay? Yeah, that is why. So manjal and vepal use panamna. It is good. Of course, this during this pandemic situation. So எல்லாரும் என்ன சொன்னா மஞ்சள் குடிங்க மஞ்சளை போட்டு குப்பிங்க உப்பு புளிங்க கோவம் மஞ்சளையும் உப்பையும் போட்டு gargle பண்ணுங்க வேப்பலை எல்லாம் வச்சுக்கோங்க அப்படின்னு சொல்றாங்க. That is because of the what is anti-inflammatory and antioxidant is there in the மஞ்சள். தமிழர்களா சிறப்பா யூஸ் பண்ணிருக்காங்க. Okay, right. Okay, again it takes some time. Okay, I leave it. Yeah, thank you so much. And
ஏன்னா நீங்கெல்லாம் சொந்தக்காரனால நிக்கிறவங்க, சொந்தக்காரல நிக்கிறவங்க, உங்களுக்கும் எங்களுக்கும் நிறைய வித்தியாசம் இருக்கு சார். நீங்க எவ்வளவு பெருசா ஜெயிச்சாலும் அந்த வெற்றி கூட உங்களுக்கு சொந்தம் இல்ல சார். ஏய், நான் எவ்வளவு கேவலமா தோத்தாலும் மீசைய முறுக்கிட்டே தோப்பண்டா.
Okay, right. So I have to thank my management, our college management, director and principal, for giving such a wonderful opportunity to deliver talks on magnetic materials and various colleges. So I have to thank them. And this is a beautiful announcement that I have a couple of PhD positions, and those who are interested in this PhD position, maybe you can approach. My email ID is at the end of the slide. My email ID is there. Those who are interested, you can approach me. But okay, right, fine. Yeah, I have my YouTube, of course, Dr. Aruldas or Geeta announced that my lectures are available in YouTube. Maybe you can visit my YouTube. I have my own channel, Manikya Mahendran. You can visit it. Of course, I am about to complete this book, these two books. Soon these books will be published. Yeah, thank you very much. Arivial Katrutanda Anaitu Osayalakum Nandri. Thank you so much. Again, I have to thank Dr. Geeta and the Nesamani Memorial College for giving me an opportunity, beautiful opportunity. Thank you, Geeta. Hello.
Thank you, sir.
Thank you. Maybe you can ask. I mean, participants can ask questions, please. Yeah, I think.
Yeah, thank you, sir. So now the participants can ask questions. You may post your questions in the chat box. I request Dr. Raisel Jayagida, the webinar convener, to read out those questions to the resource person.
So the first question is
Yeah, please go ahead.
posted by Dr. R. Siteswaran, Assistant Professor in Physics, Chennai.
Okay.
Sir, is the shape memory alloy or mixture of different materials like a composite or chemical compounds? Whether doping is possible? Give me some of the example methods to prepare shape memory alloy.
Okay, thank you, Dr. Siteswaran. Okay, thank you so much for your question. That yeah, of course, obviously, this is true that it is a mixture of different materials. Like it is a composite. Basically, it is a not a shape memory alloy. Shape memory alloy composite, you can make it. Shape memory alloy itself is not a composite. It is an alloy. It is basically a metal, right? It is, of course, what you can say. It is rightly said. It is a chemical compounds, right? So that whether doping is possible, no, doping is not possible. But by doing our trial and error method, you can have you can prepare your own alloy. That's it. So it is not a composite; it is an alloy. Of course, it is a chemical compound. Doping is not possible. Give me some of the examples, methods. Yeah, very simple. We have our own setup to prepare shape memory alloy. See, conventionally, you can use your own arc melting furnace or resistance thermal furnace, muffle furnace, whatever the furnace that you have. Of course, I have my own arc melting furnace. You can prepare your own alloy, but the question here is training the alloy is important. Alloy preparation is not the big deal, not the big task. Training the alloy, which requires a special custom-made instruments. Or I told you that to confirm the shape memory property, we need to have a special apparatus which we have designed our own setup, which is available in my lab. Yes, thank you, Dr. Siteswaran. Next question, please. How can you measure the magnetic strength of magnetic? Yeah, I'll read Gita. I'll read it out.
Yes. Okay,
How
sir.
can you measure the magnetic strength of magnetic nanoparticle? What is the self-life of magnetic? Yeah, of course. That's an interesting question. One can measure the strength by using, again, the training. We have, again, our setup like a very simple electromagnet that we have. It depends on the material can be cured at particular temperature. For this ferromagnetic sheet metal alloy, the magnetic field required to cure this temperature is 0.1 Tesla. And the magnetic property, the self-life, yeah, obviously it has. You can, one minute, principal is calling me. Professor, 5 minutes, professor. இந்த ஒரு நிமிஷம் கூப்பிடுறேன் ப்ரோ கேட்டு சாரி இந்த ஒரு கிளாஸ்ல இருக்கேன் சாரி principal has called me. Okay, right. Anyway, Dr. SIP IR, yeah, that is true. And how to check the self-life of magnetic properties that one has to use the mechanical training. That means the material can go up to, this cycle of operation can take, which can go up to 10 to the power 6 cycles. So after that, we can talk about the life cycle or the self-life of this material. Yeah, because which can make this many type of actuations. Okay, right. Yeah, the next, you may type. Whether the thin film, Siteswaran again, whether the thin films are alive. Yeah, of course, possible. Is it possible to share the presentation with us, Niveta? Okay. Okay, share it. Okay, fine. Very nice presentation, sir. Thank you. No more question. No question. Comments. Sir, could you tell a bit more about postdoc experience? Yeah. George Matthew. Yeah, of course. My visit to MIT was sponsored by our DST under the Boyskes Fellowship Scheme. The Boyskes Fellowship Scheme, what I mean is like, under Young Scientist Scheme. Yeah, of course, under Young Scientist Scheme, I visited MIT and spent, that's a really beautiful institute. Right? Yeah, just look at my screen, the desktop of laptop. This is a MIT place where my wife visited. And of course, really, it is good experience. Maybe, George Matthew, you can visit. You can call me over phone. We'll discuss more about MIT, please. George Matthew, please. Okay. Sir, can we do the theoretical studies on this material using computer software, for example, Gaussian? Yes, we did. Yeah, of course, I showed, yeah, Hannah Ruben. Yeah, it is possible using Gaussian. And we have DMOL, we have BN2K. I produced a couple of PhD on using this Gaussian. We did some research on computational materials using this software. Maybe you can talk to Dr. Shanmuga Sundari, she's working in the Stella Maris, Chennai. Yeah, she has used the software for making this computational research. Yeah, Hannah, thanks. What are the parameters to identify smart materials? Nothing, Dr. Flip. Parameters to identify, yeah, there are 4 parameters. If your research is focused on ferromagnetic sheet metal alloy, first, you have to identify whether the material obeys, whether the material is in the ferromagnetic family or not. Yeah, first condition is that. And the first important condition is you have to check the macrocrystalline anisotropy value, the Ku value. These 2 are important parameters to identify whether it is a sheet metal alloy or not. Very nice information, Bhuvneshwari. And okay, Geeta madam, no more question, I guess.
Yes, sir. Okay, sir. So the next one.
I think now my friend Dr. Vinolin, Ada Vinolin asked me a question. Vinolin, are you there? Madam? Okay, right. Only. Okay, yeah. You asked of the post the question privately. Okay, fine. Yes, you can go at Geeta, madam. Yeah, please. Geeta, madam. Hello. Hello, what happened?
Chibi, sir?
Yeah.
Yes, madam.
Yeah, just now. Yeah, right. Yeah, right now. Okay.
Shall I continue?
Yeah, please. Go ahead, please.
Okay. So now we come to the end of the session. Vote of thanks. So first of all, I am thanking our God Almighty for giving an opportunity to conduct a webinar on magnetic smart materials in a very successful way. If you want to live a happy life, tie it to a goal, not to people or objects. This is the quote by Albert Einstein. Yes, this quote is very much suitable for our smart, active, and intelligent resource person, Dr. M. Mahendran, Professor and Head, Department of Physics, Tyagarajan College of Engineering, Madurai. He is my guru, both in MPhil and PhD. Sir, you are admired by all of us within a very short period. Thank you, sir, for your very nice presentation and sharing the knowledge within a fantastic way. Sir, I also thank for introducing the Natupura Dosayum nanotechnologyum கூடவே மாறி ஆத்தாளும் மாடர்ன் சயின்ஸும் இது எங்களுக்கு மிகவும் அருமையாக இருந்தது. முக்கியமாக லேடிஸ். நன்றி ஐயா. Once again, I thank you very much for your nice presentation and thank so much for accepting our invitation and give the nice presentation. Thank you, sir. Coming together is a beginning. Keeping together is progress. And working together is success. This is the quote by Henry Ford. Yes, I express my thanks and gratitude to some personalities behind the success of this webinar. I thank our correspondent, Advocate Rajathurai, our principal, Dr. K. Palraj, our IQAC coordinator, Professor R.S.T.B. Thomas, our HOD, Dr. R. Sheila Christie, our self-finance HOD, Dr. L. Batmaja, the professor who introduced our resource person, Dr. D. Aruldas, and my colleagues for their constant support, sacrifice, and encouragement. Thank you all. I would like to thank the professors, UG students, PG students, MPhil and PhD scholars from various institutions participated in this webinar. I thank our NMCC college staff and students for attending the webinar. Thank you all. I wholeheartedly thank my colleague, the co-convener of this webinar, Dr. A.S. Jabamala, for her sacrifice and the effort taken for the success of this webinar. Thank you, ma'am. I extend my gratitude to one of the twinkling star other than NMCC family, who is the son of Dr. A.S. Jabamala, his engineer Prailin Jerish, who has supported me in the designing and editing work. Thank you, Engineer Prailin Jerish. for your valuable help, support, and effort. Once again, I thank you all. Thank you. Thank you, sir.
Thank you, Geeta Madam, and IKC coordinator and principal. And of course, I love my participants who has given me wonderful feedback on my presentation, whether it is true or not. But anyway, still, thank you so much. Bye. Shall I close it?
Yeah. Thank you, sir. Thank you so much on behalf of
Okay,
the
sir. Okay, sir. Bye.
We would like to thank you, and special thanks to the Department of Physics for arranging such a wonderful webinar with a wonderful resource person, enlightening all of us. So special thanks to the convener, Dr. Raisel J. Geeta, and the co-convener, Dr. Jebameller, the entire physics department family, the head of the Department of Aided and Self-Finance, and all the staff members. And thanks to the principal, correspondent, and all the participants present here. Thank you, one and all.
Thank you.
Thank you, sir. Okay, bye, sir. Mahendra, sir, bye.
Bye.
Bye.